Cool. So with that, I'm happy to introduce Jason Hartline. He's an associate professor in the computer science department at Northwestern University. He'll talk about approximation and mechanism design in a way that I think will tie in very nicely with previous lectures that we've seen by Kostis, by Rakesh Bora, by Eva, and hopefully this will give you a very nice and complete picture of really what's cool right now in computation and mechanism design. So thanks, Jason.
Thanks. So I want to first mention that anything that I say today is written down in course notes, which are available on my webpage, which you can download and read and check back on to see if you remembered anything I said correctly. I'm going to be talking about mechanism design, which, as you probably know by now, asks the question of how a social planner should set up the rules of a system so that good things happen in the equilibrium of strategic play. This has a number of applications in the internet, which is why computer scientists really care about it. And all of these applications, what they have in common is a general theme of resource allocation. So you have limited resources. How do you allocate limited resources to players who are strategically trying to get the most resources? Here's an overview for the two parts of this course that I'm going to be lecturing on. The first part today actually is going to be almost entirely 1970s classic mechanism design from an econ perspective. And the reason why I want to do this is because I think it's really important to have a really solid foundation and really understand what these basic concepts mean. So I'm going to focus mostly on single item auctions. I'm going to focus on two economic objectives, profit maximization and social surplus or welfare maximization. I'm going to talk about one of the main workhorses in auction theory, which is the characterization of Bayes-Nash equilibrium. And then I'm going to talk about three very simple consequences of this characterization of Bayes-Nash equilibrium. In particular, how to solve for Bayes-Nash equilibrium. If you're given a game and distributions, how do you figure out how players play? Uniqueness of equilibrium. How do you show that the equilibrium that you solve for is actually the only equilibrium? There aren't other things that you missed. And then how to optimize over Bayes-Nash equilibrium. If you're trying to design a good auction, you want the auction that has a good Bayes-Nash equilibrium. So how do you optimize over the Bayes-Nash equilibrium? Part two, which will happen on Friday, I will talk about a number of much more contemporary issues in mechanism design, in particular using approximation to say many interesting things about mechanism design. Okay, if you care how this relates to the course notes, which I pointed you to on my first slide, today is going to be mostly chapters 2 and 3. And on Friday, I'll do the entire rest of the course notes in an hour and 30 minutes. But I'll leave out a lot. Okay, so I want to start with the most simple situation you could possibly think of for thinking about resource allocation with strategic players. Suppose I have one resource, and I have a bunch of strategic players. These players have, unknown to me, private values for obtaining this resource. And they have their own strategic incentives, which is to maximize their own utility, which is the value they get for the resource minus the price they're paying for the resource. And we'd like to design an auction which solicits bids, chooses a winner, sets payments, etc. We might have two possible objectives in mind. The most common are the social surplus, meaning you want to maximize the value society gets, meaning give the object to the player who has the highest value for the resource. Or you might want to maximize the seller profit. If you're selling an item on eBay, this is probably your objective. Okay, I'm going to start with objective 1. And I'm just going to throw up some example auctions, which you've probably seen before, to talk about. So the first auction that you've seen before probably is the first price auction. How does the first price auction work? You solicit bids. the winner is the person who bids the most, and they pay their bid. So on the bid vector 2641, the person who bids 6 wins, and they pay 6. Another auction that you've seen discussed here in this summer school is the second price auction, which is almost the exact same rule, except that the payment isn't the bid of the winner, it's the next highest bid. So on this input, the person who bids 6 still wins, but instead they pay 4. Okay, so I want to now ask the standard sequence of questions that an auction theorist would ask about these auctions. And so what are those questions? The first question you would ask is, well, if I had strategic players playing in either of these auctions, what would they do? What are the equilibrium strategies? Once I answer that question, I can then ask the more interesting question is, okay, well, what should I expect the outcome to be in the auction? Who's going to win? How much are they going to pay? And then, once I've answered both these questions for both my auctions, I can start comparing them to see which auction is better. Which auction has higher surplus in equilibrium? Which auction has higher revenue in equilibrium? And then I can even try to optimize over all possible auctions, not just these two, but to try to get the auction that's the best in equilibrium. Okay, so I'm going to start with the easiest one. I'm going to do the equilibrium analysis of the second price auction, which presumably you've seen before in this week. But I'm going to do it to really accentuate what I think is the most important part of why this auction works and how we're going to use why it works in the future. Okay, so let's think about how a bidder I should bid in the second price auction. And let's do a thought experiment where we let TI be the maximum of all other players' bids. Okay? If we let TI be the maximum of all other players' bids, then this tells us exactly what happens to bidder I as a function of their bid. Right? If bidder I bids BI bigger than TI, they win and pay TI, which is now the second highest bid. If they bid below TI, then they're not a winner and they pay nothing. So to figure out this strategy, if we knew TI, it would be everything we needed to know. Okay? So what I want to do is plot this bidder's utility as a function of their bid, depending on what TI happens to be. Okay? And I'm going to look at 2 cases. So this bidder knows what their value is, and we're imagining they also know what TI is. There are 2 cases to consider. There's the case where TI is less than V, and the case where TI is bigger than VI. Okay, and let's plot that bidder's utility. So if VI is bigger than TI, then if the bidder bids above anything above TI, they win. And their utility is VI minus their payment, which is TI, so it's VI minus TI. And VI minus TI is a positive number by the assumption of the case that VI is bigger than TI. If they bid below TI, they lose and they get 0. So what we plotted here is this utility, which is some positive number VI minus TI for every bid above TI, and 0 for every bid below TI. Similarly, in case 2, if VI is less than TI, the exact same thing happens, but VI minus TI is now a negative number. So they have negative utility for winning and bidding above TI. And so now you ask, what does the player prefer? Well, they want to maximize their utility. So if we're in this case, any bid up here is fine. If we're in this case, any bid down here is fine. Okay? And it turns out that one bid in particular is fine no matter what case we're in. And that is to bid VI. In both cases, that's maximizing your utility. Okay, so bidding VI is a dominant strategy. And what I want to point out here, and the reason why I walk through this proof that you've already seen again, is because this TI I'll just call the critical value for player I. And notice that this proof didn't depend on how I came up with that critical value. I used the max of all of the bids here as the critical value, but if I replaced any function I wanted here of the other bids as a critical value, the exact same strategic implications would have happened. Okay, so what have we learned? What we've learned is if each bidder faces a critical value that they might not know, and if they bid above the critical value, they win and pay the critical value, otherwise they lose, then the auction has a dominant strategy of bidding your true value. Good. So what can we conclude from this equilibrium analysis about the second price auction? Well, truthful bidding is a dominant strategy. So what does that mean? That means this auction maximizes social surplus. In equilibrium, people should be bidding their values, and the auction, by definition, assigns the item to the player with the highest bid. But if bids are equal to values, and we assign the item to the player with the highest bid, then we assign the item to the player with the highest value. So it maximizes social surplus. Okay, I now want to switch and talk about the first price auction, which is going to be much more challenging. So how would you bid in the first price auction? And the first thing you should notice is that there is no dominant strategy equilibrium, right? You care about the highest other bid. And if your value is above that, you would like to bid just above their bid, but not any higher than you have to, right? So depending on what that second highest bid is, you have a different strategy, which means there isn't a dominant strategy that's good no matter what anyone else does. It depends on what other people do. So that's going to make analyzing this auction much more challenging. So I'm going to quickly review some probability so that we can walk through very simple examples. I'm going to use as my example today the uniform distribution for everything, which is super easy to talk about. So if I draw a random variable v uniformly from the interval 0, 1, and I'm going to denote my random variables in this light blue color so you can see what's random when I'm doing analyses later. Then the cumulative distribution function, f of z, is just a probability the random variable z is less than z. And for uniform, that's z, right? And the density function is just a derivative of that, which for the uniform distribution is 1. Good. What's the expected value of v? It's the integral of v times the density function, which is 1. So it's the integral of v, which is 1/2. It's the area of that triangle. Okay, and if I wanted the expected value of some function of a uniform random variable, that would just be the integral of the function, which would have here minus this plus that. Okay, order statistics. What if I draw a bunch of uniform random variables? How do I expect them to lie on the unit interval? Well, I expect them to evenly divide the interval. So if I drew two uniform random variables, the expected highest one is 2/3, and the expected second highest one is 1/3. Great. Okay, so let's return to the first price auction. And I asked you what you would do here, but I really didn't give you enough information to figure out what you would do here. So now let's give you some more information. Let's suppose you're bidding against me in a first price auction. Okay, and let's suppose that our values are uniform 0, 1. And let's suppose you believe I'm going to bid half my value. Okay, so my value is uniform 0, 1. I'm going to bid half my value. So my bid is uniform 0, 1/2, right? If I'm bidding half my value and my value is uniform 0, 1. So now you have everything you need to know to figure out how to bid, right? And so let's ask that question that you're going to ask. So we can calculate your expected utility, given that your value is v, for any bid that you put in. And I want to point out that your value v and the bid you put in are not random variables for you. Those are your values, you know it. And b, your bid, you determine it. These are not random variables. But your utility in the auction is a random variable because it depends on what I do. Okay? So what is your utility? Well, if you win, which is a random variable, then you get v minus b. Right? You pay b, and you get v for winning, so you get v minus b. All right, so let's calculate this. So what is the probability that you win? It's the probability that my bid is less than your bid. My bid's random. Which is the probability that half my value is less than your bid. Rearranging, multiplying by 2, it's the probability that my value is less than twice your bid. And this is just the definition of the cumulative distribution function. The probability that a random, uniform random variable is less than 2b is 2b. right? So now we just have equations, which we can solve by taking the derivative and setting it equal to 0. And you would get that what is your optimal strategy here? It's to bid your value over 2. So what did we learn? It's an equilibrium, right? Because if you assume that I was bidding half my value, then what do you want to do? You want to bid half your value. OK. Well, then if you're doing that, what am I going to do?
Same thing.
The same thing. Fantastic. So bidding half your value is an equilibrium. So what can we conclude from that? It optimizes welfare. Okay, the bidder with the highest value wins. It optimizes social surplus. Fantastic. So just some definitions of Bayes-Nash equilibrium. Strategies maps values to actions. There's a common prior, values drawn from distribution. Distribution function, probability density function again. And a strategy profile is in Bayes-Nash equilibrium if for all players the strategy is the best response when the other players play the action that's induced by their strategy and the distribution. That's Bayes-Nash equilibrium. You've seen that before. Okay. What did we conclude about surplus maximization? We saw two auctions, the first price auction and the second price auction. Both auctions maximize surplus in equilibrium. However, the first price auction only did it for IID distributions, whereas the second price auction did it regardless of a distributional assumption. Everybody agree? Good. I think this is actually a surprising result, this first result, that there's an auction that maximizes our objective regardless of the distribution. Right? It doesn't seem necessarily intuitive that that should always be the case. And in fact, it's not the case. And we'll see that when we turn to profit maximization. Any questions?
Is it easy to show there are no other equilibria for the...
We will get to that later in this discussion. Thanks for asking that. That's a great question. OK, I want to now turn to seller profit. And let's continue looking at this example situation. Two players, uniform 0, 1. And so now you should just be able to tell me, what is the profit of the second price auction?
The second highest.
Two players, uniform 0, 1. 1/3, right? Because I draw values from the unit interval, sort them in expectation of the evenly divided interval, and my expected profit is the expected second highest value, which is 1/3. Fantastic. What's the expected profit of the first price auction? The same. Why? It's half of the highest value, which is an expectation is 2/3. Fantastic. So another surprising result. The first price auction and the second price auction have the same revenue in equilibrium. Okay? I want to ask, we're going to get back to this revenue equivalence result later, but let's next ask the question, well, if these auctions have the same revenue, are there other auctions that do better? Yes?
Well, I guess my next question would be, with more players, does this also hold?
Yes.
They have the same revenue?
Yes.
Okay.
And so I'd like to get more profit, and when I ask the question of getting more profit, I will allow for reserve prices, and so let's do that. Let's look at the second price auction with the reserve price. Okay? And what is the second price auction with the reserve price? Let's just imagine the reserve price as the seller beforehand puts in a bid at R, and then if there are no bids above the reserve R, the seller just keeps the object. If R is the second highest bid, then the highest bidder pays R. If R is below the second highest bid, then the highest bidder pays the second highest bid. Okay, so strategically, it's strategically the same as the second price auction anyway, because the reserve bid behaves just like any other bid. So it has a dominant strategy equilibrium already. So let's ask the question of what the second price auction profit is with reserve 1/2 and two bidders uniform 0, 1. So it's pretty easy to calculate what this is. We'll draw values from the unit interval, we'll sort the values, and then we'll do a case analysis. There are 3 relevant cases, right? There's the case where the reserve is above both values, in which case our revenue is 0. There's the case where both values are above the reserve, where our revenue is V2. And there's a case where the values split the reserve and our revenue is 1/2, right? So we can calculate the probabilities of each of these cases, which are 1/4, 1/4, and 1/2. And then we can calculate our expected profit in these cases, which is 0, 1/2, and the difficult one is the expected value of V2 given that we're in case 2. What is the expected value of V2 given we're in case 2? These are now if I condition on them both being above 1/2, they're now uniform 1/2, 1. So they evenly divide that interval. And so this is like 1/6 above 1/2, which is otherwise known as 2/3. Okay, so I can multiply these all out and add them up, and I get 5/12 as my revenue. And you'll note that 5/12 is bigger than 1/3, which was our revenue from the second price auction. So what's interesting is that we didn't assume the seller actually had a value for keeping the object. But nonetheless, pretending to have a value, a reserve for keeping the object, gave them more money. Yes?
So does choosing reserve price only have maximize?
That's a great question. We'll also answer that later. Yes? That's the same question. But a different question would be, if that's the optimal reserve price, well, is there, again, some auction that's even better than that maybe doesn't use a reserve price? It's some other kind of auction? So that would be the 2 questions. Like, is that the best reserve price, and is there a better auction? Those are great questions. We will answer those. Any other questions?
Will we get to approve the optimal auction?
Yes.
Okay, cool.
Okay, here's the next thing I'm going to do. So I'm going to present a characterization of the kinds of outcomes that can arise in Bayes-Nash equilibrium, period. Okay? And then I'm going to use this characterization to do 3 interesting things that you guys have all been asking me to do. Well, one you haven't asked me to do, but I think you would if we got any further, which is that equilibrium of 1/2. I kind of guessed that, right? But we didn't say how we found that if we didn't have the guess that I was playing a half in the first place. So the first thing I'm going to do is tell you how to find that equilibrium strategy. The next thing I'm going to do is answer the question I was asked here of, are there other equilibria, or is that equilibrium unique? And then I'm going to answer this final question of, how do I optimize over equilibrium? Okay, and how do I find the auction that gives me the equilibrium that has the highest revenue? Good? Good. So I'm going to have some notation. So we're still thinking of single item auctions. What is the auction doing? It's getting in bids. It's computing who's going to win the auction. And it's computing payments. So I'm going to let bold x be the vector where coordinate xi is an indicator for whether player I receives the object or not. So it's going to be 0 or 1, and it's going to be 1 if they get the object and 0 if they don't. Okay? And then I'm going to let x of v be the Bayes-Nash equilibrium allocation of some mechanism on values v. And implicit here are several things: the distribution and the strategies the other players are playing, and the mechanism. Right? In order to know what the outcome is when the player's values are v, I have to know the mechanism, and I have to also know what the strategies are. But once I know the strategies and the mechanism, I can tell you what the outcome is. Okay? Let v minus I be the values of other players, not including player I. So when I cover up player I's value. And then the thing that I want to need notation for is the following. I'm going to let xi of vi be the probability that player I wins when their value is vi in the equilibrium of the auction. What does that mean? take expectation over other players' values, and look at whether player I wins or not when they have value vi and the other player's values are random from the distribution. Okay? So this is actually something that you've seen before. This is the interim probability of winning that Costas and Ricky were both talking about. Okay, this is the interim allocation rule. Okay, I'm going to also define payments in the exact same way. A payment vector, payments is a function of the values of the players and the expected payment that a player should make if their value is vi in expectation over the values of other agents. So the interim payment rule. Any questions about this notation?
What are the assumptions on that?
What are the assumptions on the distribution? It'll be a product distribution.
That's all.
Yeah. And for most of what I talk about, it'll be continuous. You might as well just assume it's continuous. So here's the characterization. A mechanism and a strategy profile in that mechanism are in Bayes-Nash equilibrium if and only if the interim allocation rule is monotone, meaning the probability that the agent wins should be increasing in their value. An agent with a higher value, take one agent and compare what happens in the equilibrium when they have a high value and when they have a low value. It better be they're more likely to win with a higher value. This should be very intuitive, right? If it wasn't the case, the person with a higher value should pretend to have a lower value. And even more importantly than monotonicity is the payment identity, which says the payments are given by this formula. And let me explain to you in pictures what this formula is. So we said the allocation rule is monotone. So here's a monotone allocation rule. Okay? What is the first term? That's their value times the probability of winning. That's the surplus generated, right? So that is given by this area, value times probability of winning. What is this term? That's the integral of the area underneath the curve. Okay, so that's that integral. And to calculate the payment, we take the surplus, subtract this integral, and we get the payment, which is the area above the curve. So pictorially, this is what's happening. This is what the characterization says. If this is the surplus generated, and this is the payment, which is what the mechanism takes, then this is the utility the player gets. Right? Because utility plus payment is equal to surplus. Any questions? From here, you can see a consequence that we observed before, which I called revenue equivalence. Any two auctions that have the same equilibrium outcome, meaning they have the same allocation rule, will have the exact same revenue because of the payment identity. It says the payment is a function only of the allocation rule, and so it has to have the exact same revenue. And so in particular, the first price auction and the second price auction, both in equilibrium, give the object to the player with the highest value. So they both in equilibrium have the same revenue. They have the same payments. Questions? OK, I now want to do something interesting with this. I want to solve for Bayes-Nash equilibrium. I'm going to solve for Bayes-Nash equilibrium using only the Bayes-Nash equilibrium characterization, and in particular, this revenue equivalence aspect of it. OK, so what happens in the first price auction equilibrium? And let's just make an educated guess, right? If you were to guess what a first price auction equilibrium would be with an IID distribution, you'd probably guess the person with the higher value should win, right? They should be bidding more. They should probably win. It's a reasonable guess. So we'll guess that higher values bid more. If higher values bid more, players are ranked by value, then the outcome is the same outcome as the second price auction, which by revenue equivalence means the payments should be the same as the second price auction. OK. Well, now let's try to figure out how players should play using the fact that we know what their expected payments should be. Okay, so what is a payment in the first price auction? Well, by definition of the auction rules, it's the probability that the bid wins times the bid. Right? First price auction, you pay your bid if you win. By definition of the first price auction. Okay, but now let's use revenue equivalence. We know what the payment should be in the second price auction. Right? The payment given your values V is just the expected second price payment given your values V by revenue equivalence. And let's dissect this term. What do you expect to pay in expectation when your values V in the second price auction? Well, if you win, you pay the expected second highest value conditioned on your winning. Right? That's exactly your payment in the second price auction. Okay. Well, so if your payment is you're probably winning times your bid, your payment is also you're probably winning times the expected second highest value given that you won, then I got a nice formula for your bid. Right? Your bid should be the expected second highest value given that you're the highest value. Given the distribution, that's an easy thing to solve for. Right? So for instance, for two uniform bidders, this says B of V should be V over 2. Why is that? Well, given that you won, what's the expected second highest value? Given that I won, my value is V and I'm winning, so the other guy is uniform between 0 and V. What's his expected value? V over 2. So that's what I bid. Okay? The last step is that given that I guessed this, and then I solved and got that answer, I should then plug it back in and verify it's in equilibrium. We already did verify the bidding V over 2 was in equilibrium, so this is the equilibrium. Everybody happy? So I used the definition of the auction, and then revenue equivalence with an auction that does the same thing to solve for the bidding strategy. Okay, any questions? Okay, I now want to answer the question about uniqueness. Okay, yes?
So in this case, I knew an auction where I knew exactly how things were behaving. Suppose I was in an auction where I didn't know a different auction where I knew exactly what to bid.
Yeah, so this approach works when you have a good guess. Basically, when you expect the auction to have a particular equilibrium, then you can solve a particular outcome, then you can solve for the strategies.
So guess and verify is the way.
So guess and verify. So I had to guess what the outcome I expected was in the first price auction.
Exactly.
But I guessed something a lot easier. Instead of guessing V over 2 like I did the first time, I guessed something much more basic, which is the person with the higher value should be winning. Okay, so that was a much more basic guess, and then I used this methodology. Okay, so I now want to talk about uniqueness of equilibrium. In particular, if the equilibrium is symmetric, the equilibrium I just solved for is the only symmetric equilibrium. Right? If it's symmetric, they have to be increasing, and then that was the increasing equilibrium I solved for it. That was the only one that could be increasing. So what I'm going to do is essentially show that there are no asymmetric equilibria in the first price auction with IID bidders. Okay? And since there are no asymmetric equilibria, that means this symmetric one we solve for is the only one. I'm going to make a non-essential assumption for the clarity of this lecture. And that non-essential assumption is that the bid functions are continuous and strictly increasing. Meaning, as a function of your value changes by a little bit, you bid more. Okay? So the first theorem that I want to show you is that if I have two players with IID values and drawn from a continuous distribution, then if I ran the first price auction with a random but unknown reserve, there'd be no asymmetric equilibrium. So here's what I'm imagining. I'm running a first price auction. Players submit bids. A reserve price is drawn at random for some unknown distribution. A reserve price is drawn at random from a known distribution, but we don't know exactly what the reserve price is. and then the player is the highest bid that wins, that beats the reserve price. Okay? A corollary of this theorem is that if I have n players with IID values, then the first price auction does not have any asymmetric equilibria. Let's see why this is an immediate corollary of my theorem. Well, player 1 and 2 face a random reserve, which is the max of the other player's bids. Right? And player 1 and 2 are IID and continuous, so they have only symmetric equilibria between them. They can't be bidding asymmetrically. Right? Well, if player 1 and 2 can't be bidding asymmetrically, well, this is a symmetric argument I can apply to all pairs of players. And so no pairs of players can be bidding asymmetrically. So this theorem gives me the corollary that there are no asymmetric equilibria in the first price auction, period. Everybody good with that? Okay. So I want to try to prove this theorem. I'm going to start with a very intuitive claim. The claim is the following. Consider some value and look at player 1's bid and player 2's bid at this value, and suppose player 1 is bidding more. Right? Suppose we have an asymmetric equilibrium, which I'm going to then try to rule out. So in an asymmetric equilibrium, there's some value, and some player is bidding more than the other player. So player 1 is bidding more than player 2 at this value v. So if that happens, then the probability of winning for player 1 should be higher than the probability of winning for player 2 at that value v. Why is that kind of obvious? Well, so let's draw a picture. So player 1 is bidding higher than player 2 at some value v. Okay, so what's the player 1's probability of winning? Well, it's the probability that player 1 beats this random reserve. I said there was potentially a random reserve. And it's also the probability that player 1 beats player 2. Well, so how do they beat player 2? Well, player 2 submits an equal bid when their value is v double prime. Right? And so what's the probability that player 2's value is less than vw double prime? Well, that's just the distribution function of v double prime. Okay? Similarly, player 2's probability of winning is the probability that b2 beats the random reserve times the probability times the distribution function at v prime, right? Because player 2 beats player 1 if player 1 is bidding below, has value below v prime. Okay? All right. But b1 is bigger than b2, right? Player 1 is bidding more than player 2, so they're more likely to beat the random reserve. Furthermore, this f of v double prime is bigger than f of v prime. Right? So both terms are strictly bigger for 1 than for 2. Strictly bigger, because it's a continuous distribution. Okay? So I've proven this. What about if they're equal? Well, if they're equal, then they better have the exact same probability of winning. And it's the exact same proof. Everybody happy with this claim? Okay. I'm now going to prove the theorem. I need one more claim first, which is, let's suppose at v that that both players are bidding the same amount. Well, then the players' utilities have to be the same at that value v. Why is that true? Well, claim 0 says their probability of winning is the same. Okay, but by definition of the auction, it's first price, so the payment is just your bid times your probability of winning. Your expected payment is your bid times your probability of winning. Okay, which is the same for both players, because it's first price. And so the utilities are equal because utility is value times probability of winning minus payment. And so all these things are equal, and so utilities are equal. Right? Okay, I proved two very, very simple claims, and now I can prove the theorem. Let's assume for contradiction that player 1 is bidding more than player 2 on some interval between v prime and v double prime. So here's the picture. There's v prime and v double prime, and the bid functions are equal at v prime and v double prime, but they separate, and bidder 1 is bidding more, and bidder 2 is bidding less on that interval. Okay, well then by claim 0, player 1 must be more likely to win on this interval. Strictly more likely to win. Player 1 has a higher probability of winning on this interval. Right? Okay. But what's the utility difference of the players? Well, remember, the definition of utility is just the integral of the allocation rule. We saw that in the Bayes-Nash equilibrium characterization. Right? The utility of the player is the area underneath the allocation rule. And so the difference in utility between two values is the integral between those 2 points of the allocation rule. So that's the utility of player 1. Okay? But this integral is strictly bigger than the integral of the allocation rule for player 2, right? Because the allocation rule for player 1 is strictly bigger than the allocation rule for player 2. But that integral is equal to the player 2's difference in utilities. Right? But these difference in utilities have to be equal because by claim 1, they're bidding the same at both those points, so to get the same utilities at those points. So the differences in utilities are equal. So that's a contradiction. Yes?
That was the case where one bidding function is just above another for the entire range?
No. Okay, but that case can be analyzed with a very similar proof to this. So this case gives you the essential characteristics of the proof, and the other n cases you can also do. Like there's also the n case of what happens if they're equal at some point, but then they separate and never touch again. Okay? So that shows that there are no asymmetric equilibrium, just using the payment identity, revenue equivalence, the fact that utility was equal underneath this area underneath this curve. Okay, I now want to talk about optimizing Bayes-Nash equilibrium. Okay, so we're moving on to our last question, which is, okay, what's the best auction? And of course, the outcome of any auction has to be in Bayes-Nash equilibrium. So since we've characterized what kinds of things can be Bayes-Nash equilibrium, let's just optimize over Bayes-Nash equilibrium and then say, okay, what auction does that? Okay, so I'm going to do this with a definition. You've seen some of this before, but we'll go over it again. The virtual value of a player is given by this formula. It's their value minus 1 minus the distribution function over the density function. Let's take that as a formula for now. The first lemma we want to show is that in Bayes-Nash equilibrium, the expected payment of a player is equal to the expected virtual surplus of the player, meaning the expected payment is equal to the virtual value times the probability of winning, the virtual surplus of the player. Now I want to follow a general approach to optimization in economic scenarios. I want to relax some of my conditions and then optimize, and then show those conditions aren't binding. Okay, so I want to optimize revenue without the incentive constraints. What's the incentive constraints? Well, we had to have this monotonicity property. The allocation rule must be increasing. Right? That was part of our Bayes-Nash equilibrium characterization. I'm going to just ignore that constraint. And I'm going to say, well, we have this lemma that says expected payment of a player is equal to expected virtual surplus. So if I just drop the incentive constraint and just try to optimize, then it will tell me to do something. And I can then check to see if the incentive constraints are satisfied. Okay? So what's the best thing to do for revenue if my revenue is equal to virtual surplus? Well, I'd like to give the object to the player with the highest positive virtual value. Right? That's a way that I could get the highest virtual surplus, which is the highest revenue. Okay. Is that allowable? Could it be an equilibrium to always give the object to the player with the highest virtual surplus? Well, yes, if the virtual values are monotone. If the virtual value functions are monotone increasing, meaning a higher value corresponds to a higher virtual value, then serving the player with the highest virtual surplus is a monotone rule. Right? And my characterization of Bayes-Nash equilibrium was if and only if. If I have an allocation rule that's monotone, then it's the Bayes-Nash equilibrium of some mechanism. Okay? So this condition of monotonicity is important, so I'll define it to be regular if this virtual value function is monotone. And then the theorem says that if the distribution is regular, then the optimal auction is to sell the item to the bidder with the highest positive virtual value. So what does that mean? I could solicit bids. I could use these virtual value functions to map bids to virtual values. Anyone whose virtual value is negative, I throw away. People who have positive virtual value, I then will choose the one with the highest virtual value, and I'll give them the object. And I have to assign payments to. What payments should I use? The ones determined by the allocation rule, but more specifically, the critical value. Right? Each player has the virtual values are monotonically increasing, right? So there's a minimum value the player could have had and still been the highest virtual value. Charge him that amount. That'll be the same one that comes out of the formula too. Okay? So that's an auction. Okay? Proof of this theorem. The proof of this theorem actually, it's kind of obvious, right? We're trying to maximize expected revenue, which is equal to expected virtual surplus. But our auction maximized virtual surplus pointwise. Given the exact virtual values, it gives it to the player with the highest one. So it's pointwise optimizing virtual surplus. We want to optimize it in expectation. So clearly, if we pointwise optimize it, we also optimize it in expectation. Okay? So I'm going to do two things now. One, this auction is still a little bit mysterious. We've answered your question of what the best auction is, but it's still mysterious. So I'm going to demystify what this means. But before I do that, I want to say a little bit about how you prove this key lemma, which is what the whole thing was based about, and how we derived that this was the right form for virtual values. Okay? And this you've seen a little bit of before. So this lemma says the expected payments are equal to expected virtual values, and the virtual values are this formula. How do you prove that? So this expectation here is actually over the value being drawn randomly. So I have a characterization which says my expected payment is given by this formula. And so I just want to calculate its expected value. What's expected value? Well, it's the integral of the payment times the distribution, right? So I end up with some double integral that I'm integrating. So take the definition of expectation, which is a double integral, swap the order of integration on this term, and then simplify it, and you'll get this formula. And each of you could do this in like a 2-minute calculation. Okay, so I now want to demystify this whole maximize or serve the player with the highest positive virtual surplus. What is that auction? Okay, and so in particular, I want to look at what it means in the IID case. So what is that auction when players are drawn IID? So who's the winner if players are drawn IID? Well, the winner is the player with the highest positive virtual value, right? Okay, so that means player I wins when their virtual value is at least the virtual value of the other players and 0. Okay, well, if it's IID, then the virtual value functions are the same, right? So I can simplify this equation to say I need my value by taking the inverse virtual value of both sides. And I say, so I need my value to be at least the highest other person's value and the inverse virtual value of 0.
That's because it's monotone?
That's because my virtual value functions are monotone, so that I can invert them. So what you observe here is that player I has a critical value, right? And what is that critical value? It's the maximum of the other player's values and this inverse virtual value of 0, right? So what auction are we talking about here? It's the second price auction with reserve, inverse virtual value of 0. It's exactly the auction that serves the player with the highest value and subject to a reserve price. Good. So for uniform 0, 1, the distribution function for uniform 0, 1 is just the identity. The density function is 1. So my virtual value formula, v minus 1 minus the distribution function over the density function, simplifies to 2v minus 1. Right? What's the inverse virtual value of 0? It's 1/2. So the optimal auction for two players, in fact, any number of players, whose values are uniform 0, 1, is to run a second price auction with reserve 1/2. Okay, let's conclude from this discussion of optimizing auctions. So expected virtual value is equal to expected revenue. That was a major lemma in optimizing auctions. The optimal mechanism is the one that maximizes virtual surplus. This is a big one, right? So when we were trying to maximize social surplus, there was one auction that was always optimal, right? The Vickery auction was always optimal regardless of the distribution. But as you can see, the optimal auction for revenue depends very crucially on the distribution. Depending on the distribution, I'll have a different inverse virtual value of 0, and I'll want to use a different auction. Okay? So the way you should look at this is social surplus is a very special objective. It's the only objective where there's generally a single mechanism that's always optimal. For any other objective, the optimal auction depends on the distributional assumptions. Okay? For IID, regular distributions, we saw the second price auction with reserve is optimal, which is a very nice theorem because if you look out in the world and you say, what auctions do people use in real life? eBay is a second price auction with a reserve, for instance. People really do use the auctions that are actually revenue optimal. So this theory of optimal auctions is actually descriptive of the practice of how people actually design auctions, which is a great sort of sanity check for a theory. Questions?
Groceries and second price auctions, right?
We don't sell groceries with second price auctions. That's correct. We use other mechanisms than the second price auction in addition to the second price auction. We use other mechanisms. And actually, one of the topics I will cover in the approximation section of this lecture, which is on Friday, is showing that actually just posting prices is a good approximation to the optimal auction, quite generally. And it gets to be a very good approximation when you have many copies of each object. So if you're a grocery store, you have many copies of each object, just putting a posted price on each object is actually a good approximation to your optimal revenue. And it's a much simpler thing to deal with than telling the people to show up and you sell your lettuce in an auction. Right? So it's not, they could get a little bit more revenue if they ran an auction, maybe, right? But not that much, and so you might as well use a much simpler posted pricing mechanism. It's a great point, and we're going to cover that on Friday. Okay, so I promised you, so I showed you three, yeah, so before I go on.
Yeah. So for other distribution, there are not IID, are there other nice options?
That's a fantastic question. Thank you for asking that. So we did solve for what the optimal auction was, regardless of the IID assumption, right? It's give the item to the player with the maximum positive virtual value, right? But that starts to look kind of funny when players are not identical, right? Because you have to compare virtual values, and you have to know the distribution exactly to compare virtual values, right? Because as we saw, the virtual value function depends crucially on the distribution basically everywhere, right? So we have to have a lot of, so one thing that's kind of amazing about this IID regular distribution result is we only need to know one number, right? We had a distribution, which is a complex object, and we were able to summarize it by one number, the reserve, and that's all we needed to know to run the optimal auction. But in a non-IID setting, we have to know a lot more. We have to know the exact form of the distribution everywhere to solve for optimal auctions. And for that reason, we don't tend to see this more general optimal auction arise. So another conclusion you could have put here is actually, well, maybe the theory is not descriptive in more general settings, where maybe I don't expect the IID assumption to hold. And that's actually another issue that we're going to talk about on Friday, which is showing that, for instance, the second price auction with reserve is approximately optimal even when the player's values are not IID. Not allowed, I'm keeping a product distribution, but I'm just saying let's keep this form which we do observe in real life and say, is that still pretty good even if we relax the assumption of IID and regular? And that's a topic I'll cover on Friday. It's a fantastic question. Anything else?
This entire analysis was sort of expected case analysis. Is there an analogous sort of high probability analysis that you could do?
So when you say it's expected case analysis, you have to notice that there are two expectations you're talking about. One is you're talking about the expected revenue of the seller, what we're optimizing. That's one expectation. And the other expectation that you're talking about is really that each player is optimizing their own expectation.
So there is no randomness in the mechanism here, right?
There was no randomness in the mechanism here.
The entire randomness comes from the distribution that the value.
The entire randomness comes from the distribution of the player's values.
So could you have a high probability result over that distribution, where you optimize instead of the expected revenue, so the optimal option that optimizes revenue with high probability, or even with. So the reason I ask this question is you're only running this option once, like this is not a repeated option setting, and you're not insisting that the number of players be very large. So how realistic is it to do an expected case analysis if you're going to have like 3 players in an option?
This is a great question, and one of the things I will talk about in the on Friday is one aspect of your question is the following. We assume we knew the distribution, right, to solve for the optimal auction. But if there are 3 players in the world, say I'm selling supercomputers, how do I know the distribution? I can't really use statistics to learn the distribution when there are only 3 players in the world who want to buy a supercomputer, right? So that's problematic. So we might like auctions that are less dependent on making an assumption about the distribution of the players. Okay? That's a different question from the question of, let's imagine a seller who maybe has risk-adverse preference. Okay? A seller wants to have some, risk-adverse preference. And I'm not going to talk about risk-adverse preferences, but I want to point out that adding risk aversion to the seller's preference makes the objective nonlinear. And nonlinear objectives are one of the biggest challenges for mechanism design. Okay, so it's a great question, and it's not really addressed very well.
Even the bidders could be risk averse, right?
The bidders can also be risk adverse. And if you want to solve for optimal mechanism when bidders are risk adverse, you're going to have to use the more complicated theory that Kostas was talking about and that Ricky were talking about of optimizing over interim allocation rules. Okay? This approach with virtual values was very simple, right? I take each player, I map them to a virtual value, and I serve the player with the highest value. I don't have to do some complicated optimization over interim allocation rules that are jointly feasible, which is what Kostas and Ricky were talking about. For players with nonlinear utility, you're going to have to do that kind of optimization. There isn't going to be a nice virtual value-based approach that's optimal. Now that said, if you want to approximate, and something I may be able to talk about on Friday is how to approximate optimal auctions when players are risk adverse using simple like virtual value-based approaches like I'm talking about here. Okay? Any more questions? These are great questions, by the way. Okay, so I want to, this proof we used to do everything, right? So it's clear, so basically it's the most important proof in all of auction theory. So I want to give you an idea for how to prove it. Okay, so remember the point was I need to show that it's in Bayes-Nash equilibrium if and only if the allocation rule is monotone and the expected payment satisfies this equation that we had before. Okay, and so I want to do three things. I want to show that the monotonicity and the payment identity imply that we're in Bayes-Nash equilibrium. And then I want to show that Bayes-Nash equilibrium implies monotonicity, and that Bayes-Nash equilibrium implies payment identity, and then I'll have this if and only if. Yes?
I want to go back 2 questions ago. The payment identity rule, it holds even if the distribution is not IID?
That's correct.
And, well, it has to be a product distribution, or it has, or any distribution?
It has to be a product distribution. So what's underlying the question that you just asked is that we're talking about Bayes-Nash equilibrium. And what does Bayes-Nash equilibrium mean? Everyone observes their own value. And then they do Bayesian updating on, given their own value, what they think the distribution of other players' values would be. And if the distribution is correlated, when I learn my value, I learn something about other players too, and I can update based on, I update my belief on the distribution given my own value that I learned. For a product distribution, when I learn my own value, I can't update anything. I don't learn anything new about other players' distributions. And that simplifies solving for Bayes-Nash equilibrium a lot. And I'm making strong usage of that simplification of Bayes-Nash equilibrium to do these things. Okay, doing the same thing for correlated distributions is much more complicated. Okay, my first step, I want to prove that monotonicity and the payment identity imply Bayes-Nash equilibrium. I'm going to do this entirely by pictures. Okay, so my claim is that if I have a monotone outcome and the payment identity is satisfied, then I must be in Bayes-Nash equilibrium. So what I'm going to show is that some player with value vi doesn't want to mimic the strategy of a player with value z bigger than vi. Okay, and so I'm going to consider that kind of deviation. So we have what we claim is an equilibrium, and I want to show you that some player doesn't want to pretend to be another player and follow their strategy instead of their own strategy. Okay, so let's define the utility of a player who has value vi but pretends to follow strategy z as the following. Well, they get their value if they win, but they get the allocation rule, the probability of winning, as if they had value z. right? And they get the payment as if they had value z. So their utility is their value times the probability of winning when they pretend to have value z minus the payment if they pretend to have value z. Okay, so what I want to show you is that this person does not want to pretend to have this value z, meaning that they have a higher utility for pretending to have their own value than pretending to have some other value. So I want to show you this number is non-negative. Okay? And I'm going to do this in this example for the case where z is bigger than vi. So let's remember the picture we had. Right? The picture we had was, well, let's look at this first term, u of vi. That is vi xi of vi minus pi of vi. Right? And so what are those terms? Well, the first term is this green area. The second term is this, the payment is this red area. And so the utility is a difference, which is all we already said was the area underneath the curve. Right? So the first term here is this area here. Great. Let's now calculate what these two terms are for bidding some value z above vi. Okay. So if I pretend to have value z above vi, then I win with some high probability. Right? And so vi times xi of z is this bigger rectangle. Right? It's vi times xi of z. The payment I have to make for reporting z is always the area above the curve. And so now to compute my utility, I subtract the two. And I realize that I'm gaining this utility, but then losing this utility, which is negative. And now I compare it to this. I see, oh, my loss is that positive area. So I don't want to pretend to have a higher strategy. Why is this area positive? By monotonicity, because this function was increasing. Okay? So monotonicity and the payment identity imply that I don't want to pretend to have a higher value. I can draw the exact same pictures, actually slightly different pictures, pretending to have a low value. I'm not going to go through the details. Good. So we've shown by pictures that monotonicity and payment identity imply that we're in Bayes-Nash equilibrium. Let's now show that Bayes-Nash equilibrium implies monotonicity. This is something that you've seen before in Ricky's talk. So how do you show this? Well, Bayes-Nash equilibrium implies that my utility for my value is bigger than my utility for some other lie. So let's take my value equal to z prime and z equal to z double prime, and vice versa, and write down the equations we get from these two. So here we write down our utility for value z prime, we pretend to have value z prime, and our utility for value z prime, and we lie and have value z, and vice versa, for value z prime, and we lie to have value z double prime. Right? And then we do the usual thing of we add these two equations together so the payments will cancel. Okay? If I add these two and cancel the payments, which are the same on both sides, then I get this equation, which says that my surplus for reporting my own strategy is bigger than my surplus swapping strategies. And you simplify and regroup, and it says that, well, this inequality implies that if zi minus z double prime minus z prime is positive, meaning this is a bigger value, then the probability of winning has to also be non-negative. In other words, monotonicity. Okay? So now you've seen that proof again. Let's now show that Bayes-Nash equilibrium and monotonicity will imply the payment identity. I'm going to do this starting out with formulas but ending with pictures. Okay, so again, we start out with Bayes-Nash equilibrium implying that my utility playing my own strategy is higher than my utility playing some other strategy. Okay? And again, I'm going to take the two cases where my value is z prime and I pretend to play z double prime and vice versa. But now, instead of adding these two equations, or adding these two equations and canceling payments, what I'm going to do is use the first equation to get a basically, what I'm going to do is solve for pi z prime minus pi of z double prime minus pi of z prime in both equations. And I'll get an upper bound and a lower bound on what payments have to be from solving for these in both equations. Okay? And in particular, I get that the surplus for this surplus is at least these payments minus this surplus. And let's see in pictures what these upper and lower bounds mean. Okay? So let's first see what this is. So this is basically z double prime times the difference in allocation from saying z double prime versus saying z prime. So let's draw that picture. So I get z double prime, which is the x-axis, and times the difference in probability of winning, which is the y-axis here. So I get that rectangle. And what is this term here? Well, that I get z prime times the difference between z double prime and z prime again, probability of winning, which is again this rectangle. Okay, z prime is on the x-axis, and the difference in probability of winning is on the y-axis. And so this is an upper bound on the difference in payments, and this is a lower bound on the difference in payments. And so this has to be true for all z prime and z double prime, right? So if this upper bound and this lower bound are satisfied for all z prime and z double prime, then what must the payment rule be? It has to be the integral above the curve. Okay? And then to get the theorem, I just start from z prime equals 0 and integrate the whole thing. Okay? So that's the proof of the most important theorem in auction theory, mostly by pictures. Any questions? Yes?
What did you use to take pictures?
LaTeX. Okay, so I'm going to wrap up. I want to conclude by mentioning sort of the wide variety of questions for research in this area that people have been looking at in detail. So what I talked about today is essentially 1970s era auction theory. Okay, so what are people doing now? And then in the continuation of this lecture on Friday, I'm going to go into detail of a lot of these things. So we solve for optimal mechanisms, but some of those, like in the case of IID and regular, it was nice and simple, but as we discussed, for non-IID, it was a complicated thing that people don't actually use. So to get a relevant theory, we would like to show that simple things that people really do use are actually close to optimal. Okay? Showing that simple things are close to optimal. And this is related to the price of energy, price of stability. It's related to stuff that Eva was talking to you about earlier this week, about showing that natural mechanisms people really do use are actually close to the optimal mechanism. She was talking about social surplus. I'm going to be talking about this on Friday for revenue. Another question which Kostas talked about yesterday was, is the optimal mechanism tractable to compute, even though maybe it's this complex thing? And what Kostas showed is that actually optimizing over interim allocation rules, the general thing you have to do to solve for optimal auctions, even in nonlinear settings, is tractable. A great result for computational mechanism design. Another question that's raised here is, I've given you mechanism design in only the very simplest possible setting where each person's strategic value was given by a single number, right? Their value for winning. Right? What happens if players are multidimensional? Can you solve, what do optimal mechanisms look like then? Can we understand them in the same way we understand optimal mechanism in a single-dimensional setting. For instance, for a single-dimensional setting, it's the second price auction with reserve. Is there a similar kind of characterization for multi-dimensional settings? Again, Kostas yesterday gave you some ideas about this, showing that it's computationally tractable to solve for them, but getting a nice simple description is actually still something that's been left undone. So I'm going to talk on Friday about getting simple descriptions of mechanisms that are not optimal, but they're close, they're approximately optimal. Again, we brought up the issue of nonlinear preferences, such as risk aversion. And you might want to know what optimal auctions are when players have nonlinear preferences like risk aversion or budgets or something. And I may talk about that on Friday if I have time. And the last thing is something I mentioned before in response to a question, which is optimal auctions are dependent on distributional assumptions. But we really like a theory which didn't require someone developing an auction to know a whole lot about the setting where the auction is going to be deployed. Right? So we'd like auctions that were less dependent on the settings. And so we'd like to come up with maybe an auction that's approximately optimal in many settings compared to the optimal auction that knew what setting it was in. Okay, so we'll talk about that on Friday as well. So I want to conclude by putting up a bunch of homework questions, and I want to pass out these homework questions. It wouldn't be school if there wasn't homework, right? We covered a lot of stuff, and I think that from the nods I saw that a lot of you were understanding what I was covering. But my experience with the classic auction theory is you don't understand it until you try to do something with it. So these 4 questions, if you work together, won't take you more than, say, half an hour. If you work alone, maybe an hour. Okay? Very simple questions. If you work through these and answer them, which are all completely doable from what you've learned today, and if you forget something, again, it's in the lecture notes, which you can just download and look at. I encourage you to do it while you're here. You can talk to me about it if you have questions about any of these questions. I'll be here tomorrow and Friday. You can ask me. Are they due on Friday? They're due on Friday, but I won't collect them. But I recommend that you do it.
Are there more great questions for Jason?
Yes.
To go back to the theorem you just used.
Which theorem do you want?
The characterization of, yes. So here the payment is the expected payment.
Yes.
And the monetaricity is we fix the other valuations, the other players' valuations. Yeah.
Yes, this is the expected payment in expectation taken over the values of the other players that are drawn from the distribution.
And then, I mean, for point 1, so the allocation rule. So
Yep.
We fix the others' valuation.
No, we don't fix the other players' valuations. This allocation rule is the probability that the player wins in expectation over the other player's values being drawn from the distribution. Both xi of v and pi of v are taken in expectation over other players' values being drawn from the distribution. Well, what you might be wondering about is there a similar characterization of dominant strategy equilibrium? Right? This is a characterization of Bayes-Nash equilibrium. And there is a similar characterization of dominant strategy equilibrium where you just say for all values of other players, this function is a function of your own value and those values of other players has to be monotone, etc. So you replace xi of vi with xi of vi comma v minus I, and you do it for all v minus I. So that would be an equivalent dominant strategy version of the same characterization. Okay.
Is there an existence in that case?
Excuse me?
Like, is there existence of such a mechanism theorem then?
So one of the things that you'll notice is that when I solved for optimal auctions, I solved over Bayes-Nash equilibrium. But the auction I got out in the end was dominant strategy. So I actually optimized over a big space, but got out something that was actually very nice. It was lying in a smaller space, so we actually got that for free. An interesting question that you should ask, though, is it always the case when I optimize in Bayes-Nash equilibrium that the answer is dominant strategy? And the answer is, in single-dimensional settings, like this, yes, but in multi-dimensional settings, no. And so, for instance, the stuff that Kostas was presenting, his stuff was, the result was in Bayes-Nash equilibrium. It was Bayesian semi-compatible. And it's not the case that there's always a dominant strategy implementation of that mechanism that he was given. Okay?